equals a few more points than what you're looking at there. Maybe like 15 points or so for the graph interpretation. So keep in mind you want to be ready by Thursday if you're a blue day, be ready by Friday if you're a white day. Okay, slope of a position versus time graph. Well, position versus time, so remember how we title our graphs, it's y versus x. So the slope is our change in y over our change in x, rise over run. So position, change in where it is, change in position over the change in time would be y over x. That is indeed our definition of the velocity. So hopefully you've seen that a lot, kind of keep asking you that every day. So hopefully you got that one down, and that's an easy one for you. All right, now remember you're going to see 10 multiple choice. I think there's like close to 20 or so on this one. So let's look here. What do we got? We have slope of velocity versus time. So our change in y over change in x this time would be delta v over delta t. That is acceleration. All right, area. Okay, so we've done some problems here recently where you'd make a graph of v versus t, velocity versus time. So you put like meters per second for velocity, seconds for time, and really if you kind of think about this, if you just graph something, let's just say it's moving at constant velocity, just moving at a nice steady speed. If you look at the way this graph is set up, just taking velocity, which is what, meters per second, I guess, so meters per second times seconds, that would indeed, it's pretty easy to see that seconds cancel. That is, you know, just finding the distance, finding the meters that something goes. And that relationship holds true for any kind of a shape that you get on your velocity versus time graph. So yeah, that area is a good shortcut. So a lot of these story problems, just taking what you're given and making a graph can really help you solve it. Yeah, so change in position is the same thing as displacement. So 3 and 4, yeah, really the same question there. Hopefully you recognize that. Really is the same question. All right, slope of a line tangent to the curve for a position versus time graph. Okay, so once again, just take a moment. It's always so worthwhile to just think, okay, what's my y? What's my x? I'm drawing, I guess, a curve on here. I don't know, I drew this one where I guess this would kind of be something slowing down as it moves. So that curve kind of levels off as you're measuring where the position is. But anyway, if you wanted to figure out how fast that was going at any instant, at any moment in time, you would find a slope of a line that touches the curve but does not cross the curve. So you would find the slope of a line tangent to that curve. And you could do that really in any number of spots for that motion, but it's at those certain times, at that moment in time, at that instant, at that certain number of seconds, you can indeed figure out the slope of that tangent line, which would tell you the meters per second at that moment, at that instant. So hopefully you got that one. Hopefully that was pretty good for you. All right, this next one still is really kind of one of the most confusing things all year for a lot of people. It's this idea that acceleration due to gravity is constant. So your acceleration doesn't change, but that your velocity does change. So how fast you're climbing, how fast you're falling, that speed will change, that climbing speed, that falling speed. I guess if you're falling, you could say your speed would increase as you fall. So really, what are we saying here? This looks like choice B to me. Looks like choice B. Very nice. All right, see if we can apply that to this next little picture here, this marble rolling up the graph. This marble rolling up the ramp, sorry. Okay, so we got going to the right is positive, going to the left is our negative direction. So remember, this whole concept of positive is just a number line, this whole concept of positive or negative. Just a number line. So just which way did you lay out your tape measure? We've had these tracks laying around on our table for a while. So there we go. Look, you can see down the track, those numbers were getting bigger. So if the numbers get bigger as we're going down the track, that means down is our positive direction. Gravity is always pulling things down towards the ground. So down is our positive direction. Acceleration due to gravity will also be a positive number. Okay. All right, now these multiple choice, these are kind of like really story problems in a way. I just kind of stuck into the multiple choice piece. So remember, the equations will be there like as you get to the story problem part of the test. For these multiple choice, if I put a few in there, you may have to kind of think about what equation you use, think about our definitions of slope that you just had up above there. But yeah, so it says the sprinter accelerates from rest. Rest, that would be your initial velocity. So that initial velocity is 0. The acceleration is 1.5. And the t, the time, is 4. So solving for VF, you get 1.5 times 4, I guess that is 6. And really, for all of our free fall problems, you can kind of make that initial velocity 0 as well, starting from rest, starting when you're not moving. Now I'm just going to add a question here. So you might see this question and it might say, well, not how fast is she running. You may say, well, how far? What distance does she run? How far does she run? So hopefully you kind of recognize that distance formula. It's really just nothing, a combination of some of those definitions of slope we went over earlier. But yeah, we'll kind of show you that. But anyway, yeah, so plug and chug here. So the distance is 1/2, acceleration 1.5. The time of 4 seconds was given. Yeah, just punch it out on your calculator. So once again, I've been trying to kind of remember to have your own calculator. I mean, this is from $1, I believe, at Dollar Tree. And I love it. So you don't have to get a nice one. iPad, if you want to use your iPad, just let me know. There's calculators built into there. If you have a graphing one you're comfortable with, that's good. But yeah, be able to use your own calculator. Okay. Question 9. It's really the same thing. If you know the time something is falling, you really also know how fast it's going. Okay, so I just used that same equation. Acceleration is change in velocity over time. Acceleration due to gravity was 10. Plugged in 2 seconds for our time. And there we are. Speed of 20. Okay. Be careful on 10. Constant velocity. Your velocity is not changing. So therefore your acceleration is 0. When things fall, the velocity increases, but the acceleration, and that's once again, that's due to gravity, that does not change. It's 10, it's a good 33 feet per second. But yeah, we'll be looking at gravity a lot more throughout the year. But right now, really, the thing we understand is things speed up, and they speed up at that rate of 10 meters a second for every second they're falling. Okay, so yeah, this kind of chicken scratch first page, we will, that'll be on our website if you want to look at it. Okay, moving on. Here we go. Still on the multiple choice. How are we doing on time? 12 minutes in. Okay, we can do this. As things fall, if they're speeding up as they fall, that means they're going to be moving farther each second. Still means the acceleration due to gravity is constant. The velocity is changing. Really the same question, just two different ways that we saw before. All right, Isaac Newton. He was in town and running around. I guess he was probably celebrating a Cardinals win or something. I don't know. Okay. Oh no, he's climbing up the arch and dropping apples. How fast is the apple going? Use our acceleration due to gravity equals delta V over t. Final minus initial. Remember our initial velocity for free fall, you can make 0. Plug in t, solve for VF. 10 times 1.75 is 17.5. Good, 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 good. Okay, Isaac Newton, what's he doing now? Uh-oh, he's going to get arrested. He's still dropping stuff out of the arch. Okay, no. But this time, how far has it fallen? It's not going to quite get to the ground. The arch is tall, but it's not. But so let me think. 1.75 seconds. Really, if you're trying to figure out distance, solve for d. Solve for d. Just plug it in. See how you do. So 1/2 times acceleration times 1.75 times 1.75. Here we get 15.3. Very nice. So that's how far something would fall if it drops for just under 2 seconds. Okay, Isaac Newton again. What's he doing in St. Louis? He's starting from rest and he's accelerating at 1 meter per second every second. So that's our acceleration. He's going to be doing that for 3.5 seconds. I guess he got in trouble for dropping apples. So he's running away. It's not 10. He's not falling. It's not, so be careful there. If someone's running, cars moving, it's not a free fall problem. So our acceleration is 1. Solving for VF and plug in 3.5 for T. So that's how fast he would go. Well, you can kind of do that in your head, but it shows a good understanding of acceleration there. Oh gosh, he's still running. Okay. Oh, this is really same question or same given information, but this one doesn't want to know how fast is he moving, how much distance does he cover, how far does he get. I don't think he's going to get very far, but let's see. So he's running. Plug in 1 for your acceleration. Plug in 3.5 for our t, and then punch it in, multiply it out. It does. What do we get? 6.1. That works. So yeah, it doesn't get very far, but yeah. Okay. So how far it goes is meters. How fast it goes is meters per second. And how much that velocity changes is meters per second every second. Alrighty, so once again, that page, I'll put that up on our class website so you can kind of look at that at your own, as you see fit. Okay, please, when you get, this is the graph interpretation. So I kind of mentioned before, I think I may make this worth like 15 points or something instead of 10. And yeah, I guess I'd want to add a question like this. So the thing, when you get to these, just take a deep breath. Think about, what am I measuring? What is the title? What are those units? What are we putting up there? Because I'll ask you, okay, here you're given a position versus time graph. You got something moving around for like 8 seconds, marking where it is, marking its position every second or so. Yeah, so here, how far did it go? That is, it's not a problem. It's just there. It's just read the graph. How far does he go? He got 6 meters away. Okay, and then he just, in 5 seconds, he got 6 meters away, and then he just stayed there. Didn't move. Right. Stayed in that same spot for the last few seconds. So to figure out how fast they were going, you use the slope, rise over run. That would be meters over seconds. Same thing for the second part, but hopefully you're kind of, like I said, hopefully you kind of visualize what's going on. The thing moved 6 meters and then it just stayed still. So yeah, that's a zero slope. It's not moving. Not moving is zero velocity. So hopefully that kind of makes sense to you. And really, if you just kind of recognize, you don't have to show work on that. But just recognize that that slope of the flat line, your change in y is zero. Your change in position is zero. Your velocity is zero. All right, now the overall average. I'm hoping, your first instinct, I know a few weeks ago, was to just take those two numbers and average them. But if you look at the times, for part A, that was like 5 seconds of the journey. Part B, that was only 3 seconds of the journey. So you really can't just add those up and divide by 2. So if I was to add, I think people see, if I was to average those, you'd get what, 0.6? That's not the average velocity. The average velocity is 0.75. It's skewed a little closer to the velocity that took up more time. So if you're moving at this part A, if you're moving at that speed longer, your average is closer to that speed. So you can just add up two velocities and divide by 2 to get the average if your acceleration is constant. In other words, if each velocity represents that same moment in time. You can't, it does work for free fall, because free fall, those velocities are instantaneous and they do represent that same instant or moment in time. But for those car problems, running around, walking around, Isaac Newton running through downtown, you can't, don't do it for that. Okay. Deep breath. Deep breath. Look at the title. Think about what's on the Y. Think about what's on the X. Okay. So these questions, once again, it's just there. It's just, it's not a problem. You're just reading the points on the graph. So initial velocity, in other words, how fast are they moving at time 0? They're moving. So it's like we did this. We put your tape down, set your car back a little bit behind the tape, and then, well, there I am, you're moving. So they're moving to start with. They're moving to start with. Moving at 2. They're still moving at 2 a few seconds later. They do speed up. Velocity, they're going to go, get going faster, and then they're going to hold that same speed for a little bit longer. So yeah, those first few questions there, you're just reading the points, reading the velocities at each time that it corresponds to on the X. So to get your delta V, to get your change in velocity, you need to find your slopes, your accelerations here. So yeah, that first part, even though it's moving, it's not changing speed. Okay. So yeah, those units, really it's just y over x, rise over run. So the units, that's where the units for acceleration really come from. Okay, next question, part E. Ooh, we do have a slope here. We do have a slanted line. It's a positive slope. Rise over run, and if you can count it, I mean counting, I'm kind of just doing the subtraction here, but really what am I doing? I'm going up 3 over 2. Yeah, I think I just like to count. Up 3 over 2. Up 3 over 2. So up 3 over 2 is up 3 over 2. Up 3 over, that's 1.5. And then once again, that was meters per second every second. It's the rate that your velocity is changing. It's tough. It's a rate of a rate. That's one of the hardest things, really. It's just a rate of a rate is tricky. Okay. How far do they go? How far? I'm gonna. You can use the area way, but I think I'm gonna use the distance formula because the idea is really any technique you want should work. As long as it's kind of consistent here. But I'm going to use the distance formula. I got the acceleration. I got the 3 to 5. That's 2 seconds. Now it's moving, so at that beginning spot, at that 3, it is moving at a speed of 2. So that's your initial velocity for that interval. For that interval, that's your initial velocity. So what do we got there? We got like 4 times 2, 7. Yes, very nice. Okay. Now you could find the area. You can kind of draw little squares and triangles right there, and the area of that piece would indeed be 7. But yeah, let's go ahead. Let's kind of, this next one, yeah, this one's kind of the displacement for the whole thing. So how far is this guy going? You could use that distance formula again. You'd have acceleration of 0 at the first part, acceleration 1.5 for that second part, acceleration 0 again. I mean, you could use the distance formula 3 different times for each piece of its motion. But yeah, actually I'm setting this up as with areas. So yeah, and really we can kind of, the motion we look at, you can do rectangles and squares and triangles. See, I'm just doing base times height, and then the triangle is 1/2 base times height. Yeah. So yeah, that first 3 across, up 2 for the first part. The little middle square was over 2, up 2, 1/2. Over 2 up 3, and then that big one I just did was what? Over 2 up 5. So yeah, base times height, that's what all of those were. Base times height, and then the triangle 1/2 base times height. But yeah, I'm just finding area for each piece. Now, so 6 and 4 is 10, plus 3, 13, plus 10, 20, 3. Tired. It's pretty late at night I'm doing this. You guys should be in bed. I'm staying up, but you guys should be in bed while well, never mind. Okay. 20, so that's your total distance, 23 meters. That is, you could think of it as your displacement, because really everything's moving in the positive direction. So yeah, that's your displacement. Very nice. Okay. Now, really, those equations that we were just using on the graphs, the same equations that we use for story problems. So let's see how these treat us. What did I say? I think I plan to give you about 6 story problems, about 20 points worth on the real test. So here, the way to think of this one, it's kind of like our little cars that we play with. But then as they're moving, just kind of imagine some of them had a little, you could turn up the speed, a little speed dial. So just imagine the thing's moving, and then maybe a remote control car is a better thing to think of. And you just kind of crank up that speed, crank up that velocity at a nice steady pace. That's what constant acceleration means. So I got my initial, it's 2 when it's crossing the tape, crank it up to 6. That took 10 seconds. So the average, and you can, with constant acceleration, you can average them out. So the average of 2 and 6 is 4. Now how much does it change? Well, it goes from 2 to 6, and what did that take? 10 seconds. So yeah, that's your change. Is that 4/10? 4/10 is your change in velocity every second. That's your acceleration. Now, how far did it go? There's really, you know what? There's another way, and I've seen a lot of people solve it this way. So yeah, I'm going to give you 2 ways to do this. Since we found that average velocity, you can use that to figure out how far it goes. You can use the distance formula too. And really what I'll show you in class, or what I may have already shown you depending on when you watch this, that distance formula, that's really just the same equation, just kind of using some substitution, and it's in kind of a useful way to look at it. So what do we got? We got 1/2 times our acceleration. That was question B, 0.4. The time was 10 seconds, so 10 squared. The initial velocity, remember, it crossed the tape while it was moving. And then that time t for 10. So yeah, plug and chug, but just remember, try to think, is this free fall? Is this something moving on a ramp, something moving on our floor, something walking around? So yeah, be careful about what the type of motion is you're trying to think about. But yeah, that other way, you can see it, that average velocity, we found that average of 4. in part A. Yeah, so it's like, I think I asked the class this. If you're driving, you ever drive to Mizzou, you drive a speed of 4 for 10, how far? You go 40, all right? So pretty easy. Go 4 meters per second on average for 10 seconds. You're going to go 40 meters. All right. Okay, 23. Let's see here. Now, just once again, take a deep breath. Think about what it's asking. Equations will be there, so just kind of start labeling what you know, what you don't know. But yeah, an important thing on free fall is you really need to know how much time these things are in the air for. So if you're given the time, that does simplify, I think, a lot. Because if you know the time it's falling, you know a lot about its motion. Now, I haven't been writing it, but just please assume initial velocity of 0. All right? And that's true for this unit 1. That changes. We'll start throwing things towards the ground, launching things towards the ground. So yeah, that will change here. But yeah, for this first unit, just we're holding on to it, and then it drops. So VI of 0. So yeah, 22, 1/2 10t squared. So yes, so I think the cheapy calculators are nice. I like it. So 22, what I need to do, divide it by 5. That gives t by itself. And then what do I do? Take square root, I think. Yeah, woohoo, square root. Hopefully you can find that button. I don't know. Really, as you go through these, just that number that, and this is kind of the way I give you the formulas and the kind of the way I've been trying to get you to think of these. The number you have in your calculator is the number you'll need for the next step. So yeah, a lot of times just hit that square root key, and that's what you would get there. Okay, that's not the answer though. Okay, we want to figure out how fast. The fast is the velocity. Okay, so that delta V, that change in velocity over time, is our acceleration. Now when it's gravity, when it's free fall, you know it. Plug in 10, assume initial is 0, solve for VF. But really, I'm hoping this is easy for you. A lot of you guys are doing this in your head more. You're getting good practice. If you know the time, a time of 2.1, your final velocity is indeed 21. Ugh, still not finished. Okay, miles per hour. It's a conversion. Hopefully you've, excuse me, been practicing these. The conversions are very repetitive too. But yeah, the whole key is writing it as meters per 1 second. Meters per 1 second. That's the whole key there. So we got meters, cancel. If I just stopped there, punch that in, I'd get miles per second. To get seconds to cancel, I got to move it up. 3,600 seconds is equal to an hour. So the whole thing with conversions, you're never changing that original number, that original value. But yeah, I think you guys have got a good handle on these. You're doing well. But yeah, so what? 21 meters per second. I think, wow, it's 47. That's fast. That's a little bit taller than our school building. But yeah, it's like something falls off the, something just a little bit taller than our building. It's like 50 miles an hour when it hits the ground. It's moving. Okay. Now leaving the ground, that's another issue. And really, we will do a little bit of rocket science later on in the year, a little bit of astronomy and space and how motion changes or what orbits are. Anyway, so yeah, we'll use these laws, these equations for motion as we change. But yeah, gosh darn it, I like these hang time problems because it really, you kind of recognize it is tough to jump and get a certain height up in the air. So it is hard to kind of fight or work against gravity here. So yeah, I think a lot of us, just about a third of the way up the meter stick, a lot of us jumped. So I think this is within that range that a lot of you guys could do this. The whole key though is to solve these as free fall. So even though it says the person's jumping up in the air, set up your vectors, set up your problem, and solve for the motion coming down. So really, they're going to fall 38 centimeters. But you have to write it in meters. You have to write it in meters. Because because you're using acceleration due to gravity is in meters per second every second. So yeah, write it in meters. Plug in 10, solve for t. Once again, that initial velocity falling. So really the initial velocity is the peak, the top. That's what that VI is. That's why it's 0. Makes the algebra a lot easier. So please, yeah, solve these as free fall. Oh, need to find my little calculator. What is that? Square root 0.38 over 5 will help. Okay, there we go. Yeah, and so really these are, I try to make them somewhat realistic, you know, based on what we're doing, based on why we're playing around here at our school. Yeah, when you jump up in the air, you're not in the air for very much time. So yeah, it is a split second. And that's why we had to just measure the distance. And for some of us, your reaction time, you couldn't time it. You can only measure the distance. Your reaction time just wasn't good enough. But yeah, if you know the time, you really know how fast it's going. All right, so that's how fast they would hit the ground when you land. It's also the speed you would need to leave the ground. So that's the same question. So that final velocity that you hit the ground with is the same as the speed you would leave the ground to get that high. Okay, it's really kind of same approach. Now I guess you need to add an equation. This was my mistake. You need 2 equations here to figure this one out. Or you could, I mean, you know, there's, yeah, because you don't know. Yeah, you just have to find that time. That's the whole key with these free fall problems, is knowing how much time you're in the air. And once you have the time, you can get everything else. So get the time. Once you have the time, then you can figure out how far he went, how far the marble went. And this is pretty. I think this is about 3 clicks. If you remember our marble launchers, 3 clicks. This is probably, depending on the spring in there, some of them would go this fast coming out of there. So let's see here. If you remember kind of filming how high the marble went, this is what that was getting you to think about. But really, we're going to actually calculate how far it falls. And if you think about it, we plugged in positive 10 for gravity. Therefore, that velocity change that we're plugging in, that delta V, needs to also be a positive. So yeah, we're going down. You're solving for how far it falls. But once again, with all of this motion that's symmetrical, if you know the stuff about it coming down, you know everything about it going up. So solve for t, what do we get? 0.48 seconds. If something falls for 0.48 seconds, yes, if you know the time, now if we know, found time, now we can find d. 10. All right, yes, 10.48. Good. Don't forget that square. I think we've kind of ironed out those difficulties, those problems. I think that's right. That's what I was getting. Now, really, you guys double check me on these. I am moving through these. I make mistakes too. Okay. People make mistakes. All right. Okay. Yes. Overall average. Now, obviously, no one's, running for 4 minutes at the exact same speed the whole time. But on average, they're going to go 1,200 in 4 minutes. So let's see here. Yeah, you guys, we've done these. It's just kind of a different way maybe to kind of think about the conversion. And be careful. Sometimes we get so worried memorizing. It's minutes. So what do I got? 1,200 over 4. And then over 1609 again. That would be miles per minute. But I need minutes to change to hours. 60 minutes is an hour. It's about how long your test should take. But you won't have to be running, so don't worry. Okay. All right, 11 miles. Yeah, it's pretty good. It's pretty good pace to be running at. If you can run that fast for more than 4 or 5 minutes, you belong on the cross country team. Or soccer, I guess. We'll give you that. Okay, or field hockey too, lacrosse, football. Maybe you can still swim. Okay, anyway, okay. But we all learned to crawl before we could learn to run. Okay. The thing with these, it's a triangle problem. This drawing triangles is huge in our next chapter. All right, we're always kind of trying, as things are flying all over the place and changing speed and curving around and not always just moving in these kind of patterns that here, we still use the same approach, but we draw a lot of triangles to break the motion up into pieces. So that's the whole reason for really giving you these. So yeah, draw your little triangle, coming south 6, east 8. Well, 6 and 8 is 14. So that is the distance. Now in physics, there is a distinction between speed and velocity. And that distinction is only really important when things turn, when things start changing the direction they're moving in. But really for now, in the approach we're taking, most of our problems, things just kind of move in a line, a straight line. But here, the straight line would actually be, that's a 3, 4, 5 right triangle. So that hypotenuse is 10. So hopefully Pythagorean theorem's comfortable. You're good with that. If not, just keep talking to me. There's plenty of time. We'll have a lot of time next week for individual help. So if Pythagorean theorem, triangle skills aren't up to speed, that's okay. We'll get you there. Ooh, so we did this. I like our new schedule. Some people complain about it, but really this was really kind of gave us more time to kind of play around and actually chase these cars and actually set up a little track and run the cars at each other. So, and this is pretty close. Some of those cars were moving close. This is like 2 of the slow cars. Most of you got one kind of medium fast or one slow, but this is 2 slow cars. So this is going to take a while. Remember, you need to be consistent here. So if our reference points are meters apart, our velocities need to be listed in meters every second. So this whole approach, it is kind of a classic algebra problem, but you just want to think about these pieces of tape we threw down in the hall. We're 25 meters apart here. If the first car moves distance d, the second car is going to move everything left over. And that way you're still writing the equations with the same letters, the same variables in a consistent manner. So velocity of car 1 is distance over time. It's going to start there. Velocity of car 1 is given. That's it. That's all we can do. The velocity is distance over time. But we can write the distance in terms of t. So, and once again, it's that whole, how long, you ever drive to Mizzou? Okay, well, yes. Velocity times time tells you how far you're going. So we're going to write the same thing for car number 2. Car number 2's velocity is distance over time. Now that velocity was 0.2. Now the distance is 25 minus d. All right, so you got to write down how far that one moves. Is everything left over? And I hate denominators, so I just got the t out of that denominator. Just kind of cross multiplied. Some people think of that. So okay. And now I know my favorite way for 2 equations, 2 unknowns, the way that makes the most sense to me is always substitution. So I am going to, instead of writing that car 2 equation, 2 unknowns, I'm only going to write it with 1. So I'm going to put 25. So I didn't write d, don't write d. I'm going to write d in terms of t. All right. So I wrote d in terms of t. And now, now when you solve, you combine like terms. So yeah, just move your unknown, your like terms, combine like terms. So that's what I'm doing here. Combining like terms. Now the thing is this really does kind of make sense. It kind of simplifies the problem a lot, but really both of those cars moving together cover that whole, or move that whole 25 meters of space. So in some ways it kind of makes sense that their velocities times time multiplied together covers that whole 25 meters of space. But yeah, that was a slow one. Over a minute there. Over a minute. That was pretty slow. Those two cars took a while. All right, so if it takes them over a minute, how far does each one go? Well, really, I mean, once you figure out the first car, you just 25 minus that for the second car. So yeah, first car, what do I got? That same velocity, 0.15. Trying to figure out how far it goes, but I do know that I know t this time, so I know a little bit more. When you know the time, really, and hopefully that's easy to solve. Just kind of cross multiply again. Multiply both sides by 71 is really what you're doing. So I think that's what I got. I hope that's right. Maybe I made a mistake. I think that's right. Okay. Now what's the next? So that's like what? Almost 11 meters. So that means the next one's going to go about 14 or so to cover the rest of that space. So it's going to be what? The first one went just over 10. Second one's going to go just under 15. Yeah, that makes sense. There we go. So those two distances add up to 25. A good check, you can take velocity, multiply it by the time, and that does tell you how far it goes. So the velocity multiplied by the time does tell you how far it goes, and that's another way to get it's 14.3. It's the same answer. So either way. All right. Take a deep breath. Ooh. Going to Grant's farm. Okay. So they got these antelope out there in the field. And a lot of open space for them to run. And antelopes are fast. I mean, those things, they're not quite cheetah fast or ostrich fast, but they're very close. Okay. And it's impressive. All right, so my favorite way is to set up a graph. You can use the distance formula. You can solve for accelerations, plug in initial velocities and times. The thing with the distance formula is every time you have a new new acceleration, you have to use that formula for. So you'd have to use the distance formula twice if you did it. Distance formula for the first 5 seconds, plug and chug, and then use distance formula for the next 10, 20 seconds, plug and chug. I think a graph is easier. The reason is because we can use that area, because this is a velocity versus time graph. So the triangle, what do we got? 1/2, the base of 5, a height of 15. 75, half of 75, 37 and a half. Faster than the calculator. Okay. That's the first 5 seconds. That's how far the antelope would go. Now he's going to hold that speed. He's sprinting. He's going to catch that rabbit. Although I think they're vegetarian, so I don't know. Maybe not. I don't know. Maybe he's just chasing them to have fun. Okay, but he's running. So the second part, base of 20, height of 15. 20 times 15 would be 300. So it's the whole thing. So to me that sounds like 337.5 meters. And that is fast. So I don't know if you've ever ran around our track at school. It's like 400. Imagine doing that in like half a minute. That's that's moving. Okay. Okay, a marble rolls down a ramp with I think we've done this, rolling a cart down a ramp. That's fair. So we've pushed these carts and marbles down the ramp quite a bit. So this is actually pretty close, I think. Maybe a little faster, maybe a little bit longer than our ramps, but pretty close. 3 ways. 3 ways. Let's just go at it. Now, obviously, we should get the same result. Oh, I just crunch, knocked the iPad over. Okay, here we go. 3 ways. Here, oh gosh, here's the first way. So what do we say? We're rolling the marble down the ramp for what, 6 seconds, and the speed got up to 0.5, I think it said. So the velocity got up to 0.5, started at 0, and that took 6 seconds. Yeah, so not very much acceleration, but that's okay. I mean, think about our little ramps, our carts. It took a while to get going. Okay, but that's our A, so that helps. We can substitute in the A into the distance formula. Same time, it started from rest, started at 0. So really, and especially if you keep those digits in there, that acceleration really was a 0.0833333333 repeating. But yeah, so anyway, it does work out to be 1.5. All right. Or there's a second way. All right, that was the first. Let's think about here. So what do we have? I forget what I even wrote down. Oh, average. Yeah, we got enough there to average out the speed. Now remember, it's speeding up. The velocity's changing. There was acceleration. But it's due to gravity, just rolling down the ramp. It's not 10, it's not free fall. But yeah, we had an initial velocity of 0. We had a final velocity of 0.5. Those average out to half of that. Quarter, 0.25. So that's my average velocity. And really, if you know on average how much it's moving for 6 seconds, well, if you're moving at 0.25 for 6 seconds, that's also same answer. Woohoo! It works. Physics works. Oh, yeah. Okay. I don't know if you're... I may have made mistakes as we went through these. Well, let me know. Okay. Let's think. You know, I say I have a hard... You probably heard me say this, but I have a hard time talking and writing. Okay, 2 things at once. Okay, let's try a third way. The graph. It's not an antelope, it's a marble, but that's okay. What do we got? 6 seconds. It got up to a velocity of, what, 0.5. And it said it did that with a nice, at a nice steady pace. The only thing letting it go down the ramp was gravity. But, okay. It's not free fall. Okay. So yeah, that's a triangle. 1/2 base times height. Base of 6. Height of 0.5. So that is 3 times 0.5. Woohoo! Same answer. All right. Very nice. Very nice. So that is the same